Example 13. An insurance company receives an average 2 claims per week from a certain factory. Find the probability that A. It receives more than 3 claims in a given week. B. It receives more than 2 claims in a given fortnight. C. It receives no claims on a given day, assuming that the factory operates on a 5-day week. And D. The company receives no claim on exactly 3 days in a 5-day week. A. Let X be the random variable, the number of claims per week. Therefore, X follows a Poisson distribution with lambda as 2. To find the probability where X is more than 3, you need to convert it into less than, which is 1 minus probability of X less than or equals to 3. And using GC, we can have the answer as 0.143. Part B. Taking note that the claims now is to be found in a given fortnight. So the time frame has been changed. So you need to define a new random variable. Let Y be the random variable, the number of claims in 2 weeks. Therefore, Y follows the Poisson distribution 4. And you are supposed to find there are more than 2 claims, which implies it is probability of Y more than 2. And again, we need to convert it into less than, which is 1 minus probability of Y less than or equals to 2. And using GC, you have 0.762. C. It receives no claims on a given day, assuming that the factory operates on a 5-day week. So the time frame now is 5 days. We need to define a new random variable. Let W be the random variable, the number of claims on a given day. Therefore, W follows a Poisson distribution 2/5. Since there is no claim, which implies the probability of W equals to 0, and using GC, you end up with 0.670. Now, Part D is related to Part C. Given that the company receives no claim on exactly 3 days in a 5-day week, we need to define a new random variable, D, which is the number of days in a week that the company receives no claim. This probability here, this distribution here, is now a binomial. Therefore, D follows a binomial, 5-day week, and no claim is 0.670, which comes from Part C. And to find exactly 3 days, no claim, which is probability of D equals to 3, and using a GC with binomial, you end up with 0.328. Take note that a binomial distribution has a fixed maximum number of successes, whereas a Poisson distribution does not. Example 14. A student is studying the distribution of bullfrogs in a large rural field where there is an average of 500 bullfrogs per 400 km square. One part of the field is identified and divided into 50 equal squares, each with sides measuring 2 km. The student wishes to model the distribution of the bullfrogs in each square by using the Poisson distribution with mean lambda. Part 1. State the value of lambda and one assumption made in using the Poisson distribution. 2. 4 squares are selected at random. Find the probability that 2 of these squares contain no bullfrogs and each of the other 2 squares contains at least 2 bullfrogs. Part 3. The student suggests using the same model or another rural field in another country. Comment on the suitability of the model in this situation. Part 1. The number of squares in the area of 400 km square will be equals to 400 divided by 4, where the 4 comes from 2 times 2 square, which is 100. Hence, lambda will be 500 bullfrogs divided by 100, that will give you 5. One assumption made is that bullfrogs are randomly scattered in each square. Part 2. Let x be the random variable, the number of bullfrogs in each square. Therefore, x follows a Poisson distribution with lambda 5. The required probability will be probability of x equals to 0 times probability of x equals to 0 times probability of x more than or equals to 2 times probability of x more than or equals to 2. And these 4 cases, you can permutate them. Therefore, you need to times 4 factorial over 2 factorial times 2 factorial. Which give rise to probability of x equals to 0 holding square times 1 minus probability of x less than equals to 1 holding square, where you need to convert probability of x more than equals to 2. And simplifying 4 factorial over 2 factorial times 2 factorial, which is 6, your final answer is 0.000256 using a GC. Now the assumption, the model may not be suitable because of the different distribution of bullfrogs in the other country due to environmental climate factors. As a result, the conditions for a Poisson distribution may no longer apply. Alternative reasons are: 1. The environment or climate in another country may not allow for a uniform occurrence of bullfrogs throughout the field. 2. The environment in the field in another country may not be conducive in the breeding of bullfrogs, and thus it is no longer considered a rare event. (4.2) Expectation and variance. If x follows a Poisson distribution with lambda, then the expectation Ex is equals to lambda, which is also equals to the variance of x. Example 15. If x follows Poisson distribution 2, find part 1, probability of x equals to 4, 2, probability of x less than equals to 3, 3, Ex equals Ex, part 4, variance of x. For A, which is quite easy to use, you can use GC, and by keying the respective lambda into the GC and calling out the Poisson distribution, you should be able to get the answer for part 1, part 2, and for part 3, since we know the expectation is equals to lambda, therefore Ex equals to 2 and variance of x equals to 2 as well. Part B. If y follows a Poisson distribution 3.5, find part 1 where y equals to 0, part 2 y equals to more than 2, part 3 variance of y. For B part 1, using a GC and lambda as 3.5, probability of y equals 0 will have 0.0302. Part 2, take note that you need to convert more than as less than, which is 1 minus probability of y less than equals to 2, and using the Poisson CDF and from the GC you should be able to get 0.679. Part 3, variance of y is equals to lambda, therefore is equals to 3.5.